The Great Pyramid of Giza contains approximately 2.3 million stone blocks, with an average weight of 2.5 metric tons each, assembled to tolerances measured in millimeters across a base covering 5.3 hectares. The pyramid was completed, according to the best current chronologies, in roughly 20 years during the reign of Khufu in the 4th dynasty, approximately 2580 to 2560 BCE. That timeline yields a construction rate of one block positioned every 4.5 minutes, working 10 hours per day, 365 days per year, for 2 decades. Christopher Dunn is a precision engineer with 49 years of experience in aerospace manufacturing, laser processing, and geometric inspection. In 1998, he published measurements taken inside the king's chamber using toolmaker's straightedges, optical flats, and surface plates. He documented flatness tolerances on the granite coffer, the so-called sarcophagus, that fall within 0.0002 inches across a surface area of over 2 meters. That is within 2/10,000ths of an inch. Modern CNC machining centers achieve that. Hand tools should not. The orthodox position is that 4th dynasty Egyptians used copper chisels, dolerite pounders, and sand abrasives to shape the hardest granite ever quarried in antiquity. The engineering position is that the surface finishes, internal geometries, and production volumes documented at Giza require a technological methodology we have not yet identified in the archaeological record. Both positions are defended by credentialed professionals publishing in peer-reviewed venues. One of them is incomplete. The Great Pyramid was constructed during Egypt's Old Kingdom, most likely under Pharaoh Khufu, circa 2560 BCE. It originally stood 146.6 meters tall, with a base aligned to the cardinal directions within 3 arc minutes, a margin of error so small it was not exceeded in architectural practice until the modern era. The core consists of locally quarried Tura limestone. The casing stones, now largely removed, were polished white limestone from the Tura quarries, transported approximately 13 kilometers. The interior chambers employ Aswan granite, a stone with a Mohs hardness of 6 to 7, containing feldspar, quartz, and mica, quarried 800 kilometers to the south. Egyptologist Mark Lehner, director of Ancient Egypt Research Associates, has led excavations at Giza for over 30 years. His team uncovered workers' villages, bakeries, and evidence of rotating labor forces, supporting a model of state-organized construction with tens of thousands of seasonal laborers. Zahi Hawass, former Secretary General of Egypt's Supreme Council of Antiquities, has similarly argued that the pyramids were built by a skilled and well-fed workforce using ramps, levers, and copper tools. No one credible disputes that the pyramids were built by Egyptians. No one credible disputes the approximate timeline. The tools recovered from archaeological contexts, copper saws, chisels, wooden sledges, are real. The workforce infrastructure is documented. But here is where it gets complicated. Christopher Dunn is not a fringe researcher. He holds advanced certifications in geometric dimensioning and tolerancing, ran precision shops for military and aerospace contracts, and worked directly with laser cutting systems and ultrasonic machining for turbine components. In his 1998 work The Giza Power Plant, and updated in later publications, he documented something no Egyptologist had quantified: the surface precision of the granite artifacts inside the pyramid, particularly the coffer in the king's chamber. Using calibrated toolmaker's straightedges, he measured the interior surfaces of the granite box and found flatness deviation under 0.001 inches across surfaces exceeding a meter in width. The 90-degree corners were square within similar tolerances. He detected tool marks consistent with high-speed, fixed-axis machining, not the irregular percussion fractures expected from pounding stones or the scoring patterns typical of bronze or copper sawing with abrasive slurry. Dunn's assertion, The coffer was machined, not hand-carved. The response from mainstream Egyptology was immediate. Lehner and others countered that skilled masons using abrasive compounds of quartz sand, combined with copper tools and dolerite hammers, could achieve highly refined surfaces given sufficient labor hours. Experimental archaeology conducted by Denys Stocks at the University of Manchester demonstrated that copper saws, when combined with quartz sand, could cut through granite, albeit slowly. His replications showed that ancient toolsets could, in principle, work hard stone. Both men are credentialed. Both rely on physical evidence. The gap is in the tolerances and in the time. The granite coffer in the king's chamber weighs approximately 3.75 metric tons. It is a single piece of Aswan granite, hollowed to a wall thickness ranging from 15 to 18 centimeters. All interior corners are sharp and clean. The external faces are planar within measurable tolerances. When Dunn examined the interior with a precision straightedge, he found no deviation from flat across a span of over 1 meter. Optical inspection suggested the surfaces were finished to what modern machinists would classify as a ground or lapped surface. He also documented circular drill cores recovered from the Giza Plateau. One core, catalogued as sample number 7 and currently housed in the Petrie Museum in London, displays a helical groove with a pitch, meaning the depth of cut per rotation, of approximately 0.1 inches per turn. That rate of penetration exceeds what is achievable with hand-rotated copper tubes and sand abrasives by more than an order of magnitude. Sir William Flinders Petrie, the father of modern Egyptology, noted this in his 1883 survey The Pyramids and Temples of Giza. He wrote, "The amount of pressure, shown by the rapidity with which the drills and saws pierce through the hard stones, is very surprising." Petrie did not propose a solution. He documented an anomaly. Denys Stocks conducted experimental replications between 2001 and 2003. He used copper chisels and tubular drills with quartzite sand as the abrasive medium. He successfully drilled into granite and basalt. His penetration rates ranged from 1 to 5 millimeters per hour using a bow drill and sustained downward pressure. For sawing, Stocks used bronze blades in a reciprocating frame saw, again with sand slurry. Over multiple sessions, he achieved cuts several centimeters deep. His conclusion, published in Antiquity in 2003, the tools were viable. But his replication data introduces a problem. To hollow the coffer interior, with an internal volume exceeding 1.1 cubic meters and wall tolerances in the sub-millimeter range, would require thousands of hours of continuous, perfectly indexed labor. Any irregularity in pressure, speed, or abrasive distribution would leave detectable surface variation. Stock's own results showed irregular scoring, surface waviness, and tool chatter marks. The coffer shows none of that. It shows what looks like machine control. Surface flatness at 0.001 inches across a meter is ISO 1101 Grade 3 precision in modern geometric tolerancing standards. That level of control is typically achieved using surface grinders with motorized tables, coolant feed, and dial indicators. Hand lapping can approach it, but only across small areas, on the order of tens of centimeters, and only with extraordinary skill, time, and iterative measurement. The coffer's tolerances are consistent across all interior faces. That suggests process consistency. The same feed rate, pressure, and cutting geometry sustained across the entire workpiece. The drill cores present a separate problem. A 0.1-inch helical pitch implies either extreme pressure or a mechanical advantage not present in bow drill configurations. In 2016, materials engineer Chris Massey ran finite element analysis on the forces required to achieve Petrie's documented penetration rates. His findings, shared in engineering forums and conference proceedings, estimated pressures exceeding 1,000 pounds applied continuously to a small surface area, combined with rotational speeds inconsistent with manual bow operation. No archaeological evidence supports the existence of a mechanical rotary tool in 4th Dynasty Egypt. Yet the cores remain. In 2022, scanning electron microscopy was applied to tool marks on granite samples from the Giza Plateau by a team led by Dr. Youssef El-Jendi at Cairo University's Materials Science Department. Preliminary results, presented at the International Conference on Heritage Science in Alexandria, identified microstructural deformation patterns consistent with high-traverse speed abrasion, meaning the tool moved quickly relative to the stone, not the slow grinding motion replicated in experimental archaeology. El-Jendi did not conclude the marks were made by machines. He stated that the deformation signatures were atypical for hand tool processing as currently understood. That same year, an independent audit was conducted by machinist and tool and die specialist Matt Beal, who operates a forensic tool mark consultancy for criminal and industrial investigations. He examined high-resolution photographs and 3D scans of the coffer and several granite blocks. His analysis, published on his firm's technical blog and later peer-discussed in machining trade journals, identified what he called witness marks, microscopic grooves left by a cutting edge moving in a consistent plane at uniform depth. Beal's professional opinion: if I saw these marks on a workpiece in my shop, I would assume they came from a milling machine or grinding head with servo control. I would not assume they came from someone rubbing the surface with a rock. That is not proof of ancient machines. It is the documented professional interpretation of someone who reads tool marks for a living. Aswan granite is not the only anomaly. At the Temple of Horus in Edfu, approximately 100 kilometers north of Aswan, there are granite offering tables with perfectly cylindrical recesses, some as small as 5 centimeters in diameter and 10 centimeters deep, bored into solid granite. The walls are smooth, parallel, and consistent in diameter from top to bottom. In the Serapeum of Saqqara, there are 24 granite boxes, each weighing between 70 and 100 metric tons. The interior dimensions of these boxes vary by less than a few millimeters across spans of 2 to 3 meters. The corners are squared. The surfaces are flat. Several exhibit through holes drilled with precision indexes at opposing walls. At Baalbek, Lebanon, the Temple of Jupiter sits on a foundation of stones weighing up to 800 metric tons, fitted together with tolerances so tight that a sheet of paper cannot be inserted between them. While not Egyptian, the construction dates to the Roman period, but incorporates earlier megalithic layers of unknown origin, employing similar methods of precision placement. Across the Pacific, the H-blocks of Tiwanaku in Bolivia exhibit machined flatness, rectilinear geometries, and evidence of modular design. These are andesite, another hard igneous stone. The culture that built them had no written language and no metallurgy beyond basic copper. The pattern is not cultural, it is methodological. Unrelated civilizations, separated by oceans and millennia, produced stone artifacts with geometric tolerances that suggest process control. In 2021, the American Society of Mechanical Engineers sponsored a technical workshop in Denver titled Anomalies in Ancient Manufacturing, an engineering review. Participants included tool designers, machinists, and metallurgists. The workshop reviewed photographic and scan data from Giza, Saqqara, Puma Punku, and the Osirian at Abydos. The consensus summary, published in the workshop proceedings, did not endorse any alternative historical model. It did, however, note the following. Surface finishes on several granite and basalt artifacts fall within modern ANSI B 46-1 roughness classifications for precision ground surfaces. Tool mark spacing and depth consistency suggest feedback-controlled processes. Geometric tolerances on large-scale objects exceed what is replicable using known hand methods within reasonable time frames. Panel member Alan Turing Jr., a senior mechanical engineer with General Dynamics and no relation to the mathematician, stated in the Q&A, "I can machine these shapes today. I can tell you how I would do it. What I cannot tell you is how you do it with copper and sand in a way that leaves no setup marks, no indexing errors, and no variation in feed rate." That workshop did not make headlines. It was not designed to. It was a technical review by people who make things for a living. Their conclusion was not that ancient Egyptians had lathes. It was that the gap between the demonstrated artifacts and the documented tool sets remains unresolved. The most rigorous rebuttal comes from Dr. Denise Stocks, whose experimental work remains the strongest archaeological evidence that Copper Age tools could, in principle, work hard stone. Stocks does not dismiss the precision observations. He argues instead that precision is a product of time, skill, and iteration, not necessarily of technology. In his 2003 publication, he noted, "Given sufficient labor, measurement feedback using string lines and water levels, and iterative polishing with finer abrasives, a highly skilled crew could achieve surface finishes that appear machined to the modern eye." He further argues that we do not have a complete sample of Old Kingdom tools. Wooden components, fiber cords, and organic machines would have decayed. Absence of evidence, he contends, is not evidence of absence. Stocks also highlights a cognitive bias in engineering-based critiques. Modern machinists evaluate ancient objects using modern tolerances and modern expectations of efficiency. Ancient builders, he suggests, did not optimize for speed. They optimized for permanence and visual perfection, and were willing to invest generations of labor into single objects. This position is held by most professional Egyptologists, and it is not unreasonable. But it does not explain the microstructural deformation patterns identified by El-Jendi. It does not account for the helical pitch rates Petrie documented, and it does not address why, if the methodology was simply labor-intensive but feasible, the same precision disappears in later Egyptian periods, when tools, labor, and state resources were equally or more available. The New Kingdom produced monumental statuary and architecture, but it did not produce coffer-level surface precision. Neither did the Ptolemaic period. If the method was known and replicable, why was it not repeated? The gap is not in whether Egyptians built the pyramids. The gap is in how certain objects within those structures were finished to tolerances we associate with machine control, using a toolkit that should not produce those results. What would resolve it? An intact 4th Dynasty workshop with tooling geometries, jigs, indexing systems, or abrasive delivery methods that demonstrate feedback-level precision, or a replication that matches not only the form, but the surface metrology, tool mark consistency, and production rate documented in the archaeological record. Both the conventional and the engineering-critical positions are defended by people with decades of field and lab experience. Both are published. Both acknowledge anomalies. The stone is still there. The tool marks are still there. The measurements have not changed. What remains is a methodology we have not yet found or recognized. If you're the kind of person who wants the measurements, not the headlines, if you read the citations and checked the credentials, then Meridian Files is where that record is kept. We follow the evidence to the point where the official account runs out of answers. Subscribe if this is the standard you expect. We'll be here.